Hello everyone and welcome to this video. Today we are going to see sprite graphics on the Tridora CPU. And because the video controller of the Tridora CPU does not have hardware sprites, they are drawn in software. And I already did this for the Christmas demo in 2024. But it was not that great. The sprites were a bit small, 16 by 16 pixels, and the animation was very flickery. And the reason for that was that the sprite routines tried to redraw the sprites at the best possible moment during the vertical blank phase. And the vertical blank phase or vertical retrace is the phase when on a CRT display, the electron beam that draws the image returns from the lower right corner of the screen to the top left corner. And if you update the video memory during that time, there is no visible flickering or tearing. The video controller of the Tridora CPU has a status flag that indicates if the display is in the vertical blank phase. And the sprite routines did check that flag. But there was a bug in my logic design, and the flag was basically inverted, so the sprite routines did not redraw the sprites at the best possible time, but at the worst possible time. This bug has been fixed for some time now, and I updated the sprite routines so that they can display 32 by 32 pixel sprites. And I also wrote a new animation demo. So let's take a look at that program. It's not that large. It uses the Sprite library and also the audio library because it plays a sound effect. And the Sprite library is called Old Sprites here because at the end of the video we are going to have a new improved version. So we are using the old one here. And then we declare some data structures. Here's one for the background image. And here is one for a sprite. It contains the position and a movement vector and some information about the animation state. And here's also the actual pixel data for the sprite with multiple animation frames. The number of frames is just hard-coded because it's just a simple demo program. Here are some global variables for the background image and one for each sprite. Also a sound buffer and some other stuff. Then there are some functions to read in data from files. Here's one for the sound effect. And here are some functions for reading the background image and to show it on the screen. And then reading the actual sprite pixel data from sprite sheet. And here is the procedure that updates the animation state. So it checks if the animation frame should be updated, if the sprite should be moved, and there are some hard-coded limits for the sprite position, so it doesn't get off screen, and that's it. Here is the actual animation loop. First, the sprite variables are initialized. Then comes the loop. until a character is available on the serial console, meaning a key was pressed. The sprites are being drawn. Then the animation state is updated. Then we wait for the vertical blank. And now that we're in the vertical blank phase, then we undraw the sprites. That is, we put the background image where the sprite was, and then we start again at the beginning of the loop. So we wait for the vertical blank to undraw the sprites at the last position, and then we draw them as quickly as possible at the new position. Then here is the main program that just loads all the data from files. And it loads the sound effect here and starts the sample playback and starts the animation, then some cleanup, and we're done. So let's see how this looks. The program is already compiled, so I can just run it. Now that does not look good at all. It's very flickery. There's also jitter. You can barely see some of the sprites sometimes. Now this is even worse than before. So what is happening here? The obvious explanation is that the sprite code is too slow to redraw all the sprites during the vertical blank phase. But why is it so slow? Sprite routines are already written in assembly language, so it should be fast. On average, the Tridora-CPU should do 7 million instructions per second, so that should be enough. So, to understand what is using up so many CPU cycles, we need to take a look at how the sprites are drawn. First, let's take a look at how video memory is organized on the Tridora-CPU. The video controller, or frame buffer controller, has a resolution of 640 by 400 pixels with 4 bits per pixel. And since the Tridora-CPU is a 32-bit word-oriented CPU with no byte access, it makes sense that the video memory is also organized as 32-bit words. There are 8 pixels in each word, with groups of 4 bits from left to right, from the most significant bit to the least significant bit. And each of the 16 possible pixel color values maps to a palette slot that contains a 12-bit RGB value, and that is used to generate an analog video signal on the VGA connector. So a 32 by 32 pixel sprite has 4 words per line, and in total 128 words of pixel data. So to display a sprite, we need to write at least that many words into video RAM. This diagram shows some sprite pixel data where the red lines are the word boundaries. But if we write our pixel data like that, we can only draw sprites at word boundaries. That is, at x coordinates divisible by 8. And that's not enough for smooth animation. So we need to shift our sprite pixels to the right depending on the x coordinate before writing it to video memory. Here's a diagram where the blue lines are the word boundaries of the original sprite pixels, and the red lines are the word boundaries of video memory. So we need to shift pixels, and since we have 4 bits per pixel, we need to shift 4 times per pixel, on the average 15 to 16 times per word. And since the Tridora-CPU does not have a barrel shifter, it can only shift 1 bit at a time, we need to do this in a loop, and for each of the 128 words of sprite data. then we can write that to video memory. But that is also not enough, because when we shift pixels to the right, some pixels will fall off at the right border and will need to be carried into the next word. Here we see a vertical stripe of shifted sprite pixel data that will be written like this to video memory. This is the spillover of the shifted sprite pixels, and this also needs to be combined with the shifted pixels of the next column of sprite data. So this is the combined data that needs to be written to video RAM. So here we already have one thing that will take a lot of CPU cycles, but that is still not enough, because we also need to combine the shifted sprite pixels with the background image, or otherwise we will have a black rectangle surrounding the sprite. If we had a monochrome bitmap format, we could just use the OR instruction to combine foreground and background pixels. But with color values, if we OR them together, we will just get wrong colors. So we need to clear all the pixels in the background that are set in the sprite, and we need to define a color value that is supposed to be transparent for the sprite pixel data. And for convenience, we just use 0. Then we need to have a mask that we can use with the AND instruction to remove all unwanted pixels. And then we can use OR to combine foreground and background. So we need to calculate that mask, and we need to do that from the shifted sprite pixels. Here is the assembly language routine that calculates the mask for a word of sprite pixels. And I would like to believe that it is already well optimized, and it has 10 instructions inside a loop. It looks at each pixel and sets mask bits if the pixel value is 0. And then this loop needs to be executed 8 times, and we get 80 instructions for each word. So that is also a lot of instructions, a lot of CPU cycles we need to spend here. So what can we do? Some other homebrew computer projects have a complicated video controller with hardware sprites, multiple layers and so on, but that is much too complicated for my taste, so I wanted another solution. Then I read about the original VGA controller from 1987 that is generally considered to have no hardware acceleration, but it does have some features to rotate and mask bytes that are written to video memory. So I designed something similar. Now there are some additional registers in the video controller that do exactly the two things that take up the most time in the sprite routines: shifting pixels and creating a mask. So these are the new registers. There is the shifter register where you can write the pixel data. Then we have the shift count register where you write the amount of pixels to be shifted. And after you have written the shift count, you can then read back the shifted pixel data from the shifter register. Also, there is the mask gen register that is very simple. You write the pixel data into the register, and then you can read back the mask value. There are two additional registers to make things easier. The shifter mask register directly gives you the mask of the shifted pixels, and the shifter spill register gives you the spilled pixels that need to be carried to the next word. And all these registers do not interact with the video memory at all, because otherwise it would have made accessing the video memory much more complicated. Also, this way you can use these registers to draw into an off-screen buffer. All in all, the logic design for the new registers is relatively simple. This is the whole Verilog code. There are some more lines to declare some stuff that is like variables, but this is all of the actual code. And you can see that it is enclosed in if-defs, so it can be easily disabled or enabled. Now I have rewritten the sprite routines to use the new registers. And for comparison, this is the old assembly language code for calculating the mask. And this is the new code. It's not even a subroutine anymore, and there's also no loop. So it's 5 instructions instead of 80. And the code for shifting the pixels is similarly affected. It is a bit long-winded, so I won't show it here, but it is also much shorter and has less loops. Okay, now let's see how our demo program looks with the new sprite routines. Here is the new program, which is exactly as the old one, except that it uses the new Sprites library. And it is already compiled, so I can just run it. Now, that is much better. Smooth animation, no flickering. It is still not perfect. If you look closely, one of the rockets disappears when it gets to the upper border of the screen. So the sprite routines are still not fast enough to completely redraw all the sprites during the vertical blank phase. But because the time spent redrawing the sprites is now constant, it does not depend on the x coordinate anymore. There is no flickering. This could be solved by drawing the sprites in a different order, because this is the sprite that is actually being drawn last, even if it is at the top of the screen. But still, I would say that this is a big improvement. And there you have it. Smooth sprite animation with a tiny bit of hardware acceleration on the Tridora-CPU. And now I have to think about ideas for a nice game using these sprites. And that's all for today. Thank you for watching, have a nice day, and see you in the next video.